Not a clue.
Yeah, well, there's that. That might be. Oh, yeah. Oh, and you're not representing that.
Right, so this.
Oh. Yeah.
When am I representing myself?
Yeah.
When am I representing the branch? When am I representing NASA?
I'm not gonna do anything. I'm just gonna.
Every Latino should be around.
Well, that is true. I never.
Right now, yeah.
Don't be paid, but they should. They are telling me on having something to do.
Then they're going to, and I'll just bring that up. You tell me when. and then. Oh, anytime.
I think they'll ask.
Yep.
Yeah.
I don't. I'm not anymore. I was.
So welcome, everyone. My name is Walter Kiefer. I'm the Associate Director here at LPI. And so on behalf of Lisa Gaddis, the Director, I would like to welcome you to I believe this is the third of our cosmic exploration events for this school year. This is about Venus. I think it's going to be a very exciting program. I will simply tell you that the next one is scheduled for, I believe, April the 6th. It will be about the early results from the James Webb Telescope as it's applied specifically to the solar system. So this year's theme has been a march through different interesting parts of the solar system, and Venus it's my love, at least for planets. Let's be clear about that. I'm going to shut up now. But I want to welcome all of you, and I'm going to turn it over to Dr. Candy Jessup from the Southwest Research Institute, who has led the conference that's been here this week and is going to introduce the setup for tonight's public event. Candy.
Thank you, Walter.
Good evening, everyone. Thank you, Walter. Hi. So as you said, my name is Dr. Candace Lee Jessup, and everyone calls me Candy, and that's just fine. In fact, I rather like it. So we do want to welcome you to tonight's event. I am a lead scientist at Southwest Research Institute. I focus on planetary atmospheres, but what I really do is think about how planets work as a system. I'm also one of the science study team members for the ESA-led NASA-supported Envision mission. This week, I've been convening the Venus Surface and Atmospheres meeting, which has been a gathering of planetary scientists focused on thinking about the Venus planet as a system, how do clouds form, how do geologic events impact the atmosphere, how do atmospheric events such as wind impact the surface. We've been having a really great time, a lot of discussion. It's been hard to get people to leave the room. We've been enjoying our chit chat, and tonight we're going to invite you into that conversation. Before we do, I just want to acknowledge the people who've made it possible. Walter just stood up, but absolutely we are very grateful to LPI for hosting us and providing all the support. Lisa Gaddis, I believe, is in the room somewhere. She is the director, and oh, there she is. Sorry, it's hard to see because the light's right there. And then, of course, Walter, who is the associate director. I also want to acknowledge our sponsors, Lockheed Martin, who is, of course, supporting all of the NASA-led missions, and my own host company, Southwest Research Institute, which has provided financial support for some of our panelists to travel and be a part of tonight's evening. So that's all the introductory material, other than tonight's event is going to be led by our two moderators, Dr. Alan Truman, who's a principal scientist at the Lunar and Planetary Institute. He studies planetary materials, moon rocks, and of course, the crust-atmosphere interactions at Venus. And then our other moderator, Dr. Vicki Hansen, who is a senior scientist at the Planetary Science Institute and also emeritus professor at the University of Minnesota. Her work focuses on early Earth and Venus evolution. So with that, I'm going to turn it over to our moderators. I believe Vicki will begin.
Thanks very much, Candy. So I'm going to jump right in here and hit the microphone. I hope not to continue. I'll probably do that several times. So here's our solar system. We're going to focus on the inner planets today, and really the two most important planets. But I want to start with, why do we do what we do? And when I say we, I mean all of us. We are curious, we are explorers, we are scientists, all of us. How do we do it? Well, we make observations, and then we make up stories, formulate hypotheses. And those hypotheses make predictions, and then we collect more data to test those predictions, and then we make new hypotheses, new stories, we collect new data and reiterate over and over. Just wash, rinse, repeat. We never get to an endpoint of figuring everything out. I want to shout out to all of you young people here, virtually and in the audience tonight. You guys are the most important people here, because we need you guys. We're up here, some of us are getting old, and missions go for a long time, and we need you to be the ones to take on and devise missions for the future, and to be the people to pass the baton to future generations. So if you're young in particular, listen up. So we're going to go to these terrestrial planets, the rocky planets. And this looks like, oh my God, I didn't sign up for a undergraduate lecture. All of this stuff is just things we want to bring to the front of our brains. So what I have here is a, oops, my mouse isn't working. So all of the circles are a cross section through a cartoon planet. In the center, we have the rocky parts of the planet. We call that the endogenic part of the planet. Outside of that, we have spheres of atmosphere, water. Everything from that surface upward is exogenic. Things come to that planet. Bolides bring material. The sun brings energy, heat. But inside the planet, we also have a lot of heat. And when we talk about how does a planet work, that's fundamentally what we're trying to understand. What we're really saying is, how does the planet cool? How does that internal heat get out? Well, heat is transferred in different ways. Convection, if it's a fluid or can flow, it can convect, very efficient way of transferring heat. If it's a solid, a brittle solid, it's conduction. That's like taking your hand and putting it on your belly. It's an inefficient way of transferring heat. The lithosphere, the rock sphere, conducts heat. Notice that it has convection on the inside and convection on the outside. Also about the lithosphere, it's at the boundary between that endogenic and that exogenic, and the lithosphere, rock sphere, is what records the most robust record of a planet. So it's really important for that reason. So here are our terrestrial planets. This is not a cartoon. It has those spheres to scale, except for anything above the lithosphere, because we wouldn't be able to even see them. And the first thing I want you to see is that if we think about how does a planet cool, well, there are two little planets that I call weenie beans here, Mercury and Mars. They're going to cool really quickly because they're small. So we're not going to talk about them tonight, because if we're trying to understand how planets cool, we want to look at the two stars of the show, Venus and Earth. And we can see that they look pretty much the same on the inside. Okay, so Earth currently cools itself by an incredible global process called plate tectonics. And plate tectonics has all of the reservoirs, all of these spheres interacting with one another and transferring materials from one to the other. Plate tectonics, we form new oceanic lithosphere, that outer sphere, at the spreading centers. That releases some heat. Then that ocean lithosphere is subducted back down to the mantle, kind of like taking your cold hand, putting it on your warm belly, and that cools the mantle and cools the planet. We also have volcanoes that are associated with this. You see chains of volcanoes above the subduction zone, very explosive volcanoes. And then long linear chains of volcanoes in the rift zone and at the mid-ocean spreading center where we're making new ocean crust. So tectonism, deformation of the planet, and the volcanism are really tied together in this beautiful cycle. Now, there's one other style of volcanism on our planet, and that is Hawaii is a fantastic example. It is not part of plate tectonics, and it is fed by a plume, a thermal blob in the mantle that comes up all the way from the core mantle boundary. And but you can see it's not tied to plate tectonics. So when we look at plate tectonics, we have these lithospheric plates. They move in different directions and at different speeds across the planet. They are why our continents change shape, change position with time, geologic time, not human time. We can tell that there's no other planetary body in our solar system that has plate tectonics. How? Here's just 3 signatures that we could see from outer space. The first one is called bimodal hypsometry. The little plot on the left shows that basically if we look at the elevations or bathymetries on the Earth, we have 2 populations. The oceans sit low, the continents sit high. Bimodal hypsometry. We have long linear topographic highs in the oceans where we're forming that new ocean lithosphere. And we have long linear topographic lows at the subduction zone where it's being recycled to the mantle. That lithosphere, oceanic lithosphere, is recycled round numbers every 200 million years. That sounds like a short time, but the planet is 4.5 billion years old. So that's pretty quick. Well, what plate tectonics does is it basically destroys a record. Remember, it's that lithosphere that holds a record. It's like it's ripping it up every 200 million years. The other thing that's interesting about our planet, it wasn't born with plate tectonics, and we don't know what it did before plate tectonics, and we would like to know. So what might we do? We might go to Earth's sisters. Sisters hold and tell secrets about one another. I know I have several sisters. And what's so incredible about Venus and Earth is they're similar in size, density, composition, heat budget, and location in the solar system. Those are all critical parts of how a planet works. They both follow the known principles of chemistry and physics. It's the law. We make them do that. They were both born in the same day, Thursday afternoon, 4.5. I think it was 2:30, but it may have been 2:45, 4.5 billion years ago. And they both changed through time. Just like sisters, when were they the most similar? Early in their childhood. And remember, Venus doesn't have plate tectonics. So let's look at these two sisters a little more closely. So we already saw their insides. I'm going to say that's just below their skin. They're pretty similar to a first order. And the size of that lithosphere that you can't see very well, it's an average thickness of 100 kilometers for both planets. So their inners look pretty similar. What about the skin itself? Not talking about the lithosphere, but right there on the skin surface. We think that both of them have a very common rock type, which we have on Earth, basalt. And that's what forms the ocean crust of Earth. And we think this because of the Soviet Venera mission that landed on the surface of Venus. Really amazing feat just in and of itself. Now, above the skin, the planets get very, very different. Thankfully, we're not on Venus. The atmosphere is very dense CO2 and some other pretty nasty gases thrown in at the surface. Look at those conditions. It's hot, it's high pressure, it's ultra dry. And CO2 is a supercritical fluid. That's what we use for dry cleaning clothes or extracting the caffeine from coffee beans. So if we look at Venus, the shape of the surface is also very different. This is all the, what we're seeing there is the shape. Remember that Earth, down there in the lower corner that's covered up a little bit, there's our bimodal hypsometry. Venus, up in the upper left, is unimodal topography. It just makes one peak, not two peaks. So we have high regions. They're as high as the highest places on Earth. We have the lowest places are similar to the lowest places on Earth. But most of the planet sits at the same elevation. Also, if we look at the patterns of the elevations, we don't see long linear highs and we don't see long linear lows. Remember, we saw those with Earth for plate tectonics. So here we are with these two planets. And what we're going to ask our panel today to compare and think about Venus, really so we can understand more about Earth. But I want you to think about Venus in these different spheres or reservoirs. But all of our hypotheses, all the stories we make go back to data. And here's just an incredible data set that we have from the NASA Magellan mission of radar. So with that, I'm going to turn things over to my co-moderator, Alan.
Thank you. Yeah, thank you very much. So for the rest of this session, we're going to have a panel discussion with our panelists who are sitting up in front. Ask them a series of questions with short, thank you, with short replies. And then we'll open up the floor to all of you to ask questions. So let me first go and introduce our panelists. And just to be different, I'm going to do it in reverse alphabetical order. And I see Dr. Witten. Dr. Jennifer Witten. She's at Tulane University, obviously an expert in Venus and particularly in radar and geomorphology, and she is the deputy PI of the Veritas mission, which is one of JPL's. Okay. All righty. Next in reverse order is Dr. Matthew Weller, Matt, who is he's a postdoctoral scholar here at the LPI, and his interests are in geophysics and broad scale convection models, how a planet wiggles around inside and how heat, well, it's not exactly a formal phrase, but anyway, how a planet works inside. Okay. Next is Dr. Tracy Gregg, who is at the University at Buffalo, New York. She's a volcanologist primarily, working on Earth and Venus, a lot of analog work there. And then finally, but not of course the least, is Dr. Justin Filiberto. He is a manager at Johnson Space Center in the Ares Division of Research. He's a co-investigator on the Da Vinci mission, which is a lander, a probe to the surface. And he used to be on the staff here and used to be my postdoc many ages ago. Okay, so there's our panel. And then what's going to happen now is we have a series of questions that we've primed the panel for. And Vicki and I are going to alternate asking the questions, and each question will be answered by two of the panelists, and we hope to get some interesting different. So question number 1 says, we have studied Moon and Mars for a long time. Why has it taken so long to study Venus? And why is it so important to learn about Venus despite the challenges it presents? Dr. Gregg, you are first.
So during the space race, just out of luck, a lot of the Soviet missions to Venus were great successes, while the Soviet missions to Mars were failures. And the converse was true for the United States. A lot of the US missions to Venus failed, and the missions to Mars were incredibly successful. So from early on, we were building on the history of space exploration. One of the other challenges with Venus is that it is covered with all these clouds that you can't see through. So if you were lucky enough to be in a spaceship and fly by Venus and look out the window, it would be very pretty, like flying over Houston on an overcast day. And so it requires additional technologies to be developed. But it is absolutely vital that we do study Venus for all the reasons that Vicki said. It is trying to tell us something about the way the Earth was when it was a baby. And the Earth has, like so many of us who want to reinvent ourselves, destroyed its early history. And so if we really want to understand Earth and how we got here, we have to start with Venus. And because of the histories and the technological challenges, we have wonderful data from Venus from the 90s, and we haven't been back since. So we're really looking forward to going back and answering some of these questions.
Thanks. Dr. Witten, you are next up.
My turn now, huh? Okay. I largely agree with what Tracy said. So I think that, it's not very fun, huh? Anyway.
Want to take the time.
Oh, I'm taking it. I'm taking it, Alan. So I will sort of reiterate what Tracy said. It's really fun to think about these different space programs, the Russian Space Agency, NASA, and how they opted to pursue kind of different planetary bodies to start. And there was momentum there. And so that kind of people sort of stayed in their lanes a little bit, I think was part of it. I also think that it is incredibly difficult to go to Venus, not only to peer through the atmosphere, but to get to the surface. So something that Vicki spent a little bit of time talking about was the surface is a miserable place to be, right? You will be crushed and burned and bathed in toxic gas, right? Like not a fun place to be. So the longest that any lander survived was about 2 hours. So, you hear about Mars rovers, right? And they're like, we have exceeded our mission duration by 10 years.
It's not gonna happen on Venus anytime soon. I live for the day that that happens on Venus, but it will take some time because it is very difficult to survive on the surface. So you have to come up with really special technologies for powering some sort of lander or rover, for moving it across the surface. So that is one of the challenges. And before I lose my time, it is very important to understand not only Earth's past, but a little bit about where we're going. So, climate change, how we evolve, how atmospheres evolve, and how that occurs in different environments. The beauty of Venus is same size, same general composition, but very different ending place. Well, it's not really the end, but present day.
Perfect.
Did I do justice?
I thought that NASA was just saving the best planet for last, but.
Oh, I like that. That's a good answer.
Okay, so the next question is Venus has an incredibly dense CO2-rich atmosphere. It traps heat from the sun and slows the release of heat from Venus's interior. The atmosphere makes Venus a hell not on Earth. Has Venus's atmosphere always been like this, or was it different in the past? And what data tells this story? And we're going to go to Dr. Filiberto. Can somebody, oh, you've got the microphone. There we go. Yeah, you guys are so good. Here for now.
We haven't disagreed yet. Then we'll hug microphones. So it's an interesting question of what did Venus look like 4.5 billion years ago? And as Vicky alluded to, siblings act alike the most when they're the youngest. And so the models for Venus are that its atmosphere was a lot different 4 billion years ago when it was a lot more Earth-like. Where do we have data from? Well, we have a lot of old data, as we've heard. But one of the places we look on Earth is our rock record. And while we don't have a rock record on Earth going back 4.5 billion years, we do have rocks on Venus that we think are much older. And so we can look at those. We can't actually sample them, but we look at them from orbit with what measurements we can get through the cloud deck. And Vicky showed the nice view that was circling of the Magellan radar. We have near global radar images of the surface, and we can look and pick apart the rock layers and look back in time, just like we do on the Earth. The evidence we have suggests Venus was a lot more Earth-like. It may have even been habitable. There's questions about whether it had an ocean on the surface 4-point-something billion years ago, and then it dried out through time. And that's one of the reasons we're going back and sending all of these missions to go look back in time at Venus and figure this out.
You want to pass the mic down to, oh, boy, you guys are way ahead of us. That's easy to do. Dr. Weller.
All right, so the first thing I'm going to say is I agree with Justin. Now I'm going to expand a little bit. One of the interesting things about Venus versus Earth that we've heard is that Venus has this really thick atmosphere. It's 90 times Earth's atmosphere. Question is, how did it get it? So on the Earth, if you were to cook off all of the rocks on the surface in the sediment cycle, so all of our sandstones, limestones, stuff like that, over all of geologic time, you get pretty close to 90 bars of atmosphere, which is Venus's atmosphere 90. So it seems to suggest that maybe Venus didn't cycle the same as the Earth, and that's how we have different atmospheres. And then the question is, how did it get there? Justin was focusing in on the rock record, but I'm going to actually say that one of the best ways, I think, to get at the time integration of Venus, its evolution, actually the atmosphere. Because if you cooked off everything on the Earth, everything on the surface gets put into that atmosphere. And if it's in that atmosphere and you can send a probe in like Da Vinci's doing, you can actually sample that, well, everything that came before. Now it's difficult to disentangle it because it all gets put into a soupy mess. So that's why we need to get to the surface as well. But the reality is the atmosphere probably contains a rather strong record of Venus's specific evolution. And being able to understand how Venus got to be the way it is is probably locked away in its atmosphere just as much as it is in the rock record. And with that, I will see the rest of my 15 seconds.
You actually have a little more time if you have anything else to say. Okay.
Okay. Well, we'll take that time and give it to. We'll take that time and give it to the audience at the end then.
Yes.
Okay, thank you. The next question, Venus as a planet is currently bone dry. That is to say, there's no surface water. Has Venus always been so dry, or was it different in the past? And what data tells us about this past? And we go right back to Matt Weller, who's our first.
Range, it's almost like I set that up. So Venus is currently dry at the surface. That's not to say there isn't water in the atmosphere. It's probably there. We have detections of it. It's just small. It's very, very, very minute compared to everything else that we see. And because of that, the real question is, did Venus have a water budget similar to the Earth? Did it have oceans? If it had oceans, did it have life? And these are really the fundamental questions we're trying to get at. Now, why is Venus bone dry? There are a lot of different ideas. One idea is the building blocks were different between Venus and Earth early on, that Earth got more water than Venus did. Another idea is that there was effectively a great climate catastrophe that happened, maybe linked to the internal, that maybe Venus has evidence of the surface being kind of churned over and destroyed actively at some point in its past, whether it be 200 million years ago when dinosaurs roaming the Earth, or a billion years ago before we had anything more than single-celled organisms. And when it did this, it would have actually churned up a lot of material into the atmosphere. So you bring stuff up, it melts, and it releases a lot of gases. And if you release a lot of gases, you can potentially lose a lot of it to space. So it's possible that Venus actually lost its atmosphere, or lost its water to space. And one of the things we're going to look for is basically deuterium to hydrogen, which is heavy water to just hydrogen atom. And that'll tell us fundamentally if Venus had a lot of water to begin with, or if it didn't. And if we know that, we can kind of tell some of how it evolved and if life was even possible in the past.
Wow, was that perfect or what?
Okay, Dr. Filiberto, point counterpoint.
It is back to me. So I'm going to disagree with Matt.
Oh.
Not really. So one of the things as a geologist we do is we look at the rock record. And there are these weird rocks on Venus called the Tessera. And Vicky showed the map. These are the high areas. These are what we call continents on the Earth. If we can figure out what makes those, because we think those are the ancient rocks on Venus, that will help us tell about climate. As Matt talked about, was there a water cycle? Was there lots of water in the interior? Was there an ocean? Well, on Earth, what most of our continents are made of is a rock called granite, the rocks you have in your countertops. Granites require water in the interior. If these tessera, if any of them represent large granites like we have on the Earth, that tells us that back 4 billion years ago, there was a lot more water in the interior. Where there's water in the interior, where there's granites, you likely have an ocean as well. So with Da Vinci, this is one of the things we're going to do. We're going to come down over one of these tessera. We're going to get below the cloud deck. We're actually going to take pictures, because once we're below the cloud deck, we can actually take images, and see these rocks and tell what they are and see if they're granite, see if they're the ancient rock record, to see if they give us evidence of water in Venus's.
On to the next question. And this will be for Doctors Whitney and Dr. Gregg. Venus does not have plate tectonics. That's the Earth's global process that drives most of its mountain building, earthquakes, and volcanism. What is Venus's current global tectonic style, and has its tectonic style changed through time? And of course, what data tell that story?
Great question.
We put them together well.
Yeah.
Short answer, we don't really know, which is part of the exciting part, right? Like, sort of feel like Indiana Jones, but geology style. So Venus is a bit of a mystery. So there are a couple of options for the tectonic regime that it is currently experiencing. So we know that Earth has plate tectonics, that the hard, rigid part of Earth's exterior is broken up into plates that move around. Some of them crash into each other, some of them subduct or go underneath one another. On Venus, there are hypotheses that there are small rigid plates that sort of jiggle past one another. And there are some ideas that there are areas in the mantle that are very, very hot, and they bring a lot of hot material all the way up to the surface. And it's something called heat pipe tectonic regime, where you get a lot of volcanic activity associated with these hot areas. There's also an idea, the moon and Mercury and maybe Mars, which, you know, we're not talking about them, but they have a single plate. So their whole exterior is one rigid shell. And that's called sort of stagnant lid. It's a fun term, as opposed to a mobile lid, which is what plate tectonics is. And so right now there are some debates about whether or not Venus is in a stagnant lid or a mobile lid regime. And before I run out of time, the short answer to what has it changed? Yes. We know that the temperature of the planet has changed over time, and therefore the heat going from the inside out is going to affect that rigid exterior. If it's hot, it'll behave in a more kind of squishy way. And if it's colder, it will behave in a more brittle way. And so that temperature of the planet and how it changes over time impacts whether you're going to have these rigid plates or you're going to have squishier plates that move around. So, okay, great.
And on to Dr. Greg.
Not much left to say. No, no. I always have more to say. So yeah, so Vicky gave us a great introduction to plate tectonics on Earth, and Jenny just described that that's not what we see on Venus, and we don't really know what's on Venus. And one of the great mysteries and why we're still uncertain about Venus's history is, and everyone's alluded to the fact that the surface on Venus, on average, is only about, brace yourselves, 1 billion years old. What? Okay. On Earth, as Vicky said, the youngest rocks are being made at the ocean. They're being born today, and at volcanoes, they're 0 years old, right? And the oldest part of the ocean is a couple 100 million years old. The oldest rocks on Earth, rocks, not minerals, the oldest rocks are actually not far from Lake Superior, where not far from where I live, where, yeah, Vicky, okay. And they are not quite 4 billion years old. So we are largely on Earth missing the first 1 billion years of our history. On Venus, we're missing the first 3.5 billion years. Something happened to the surface of Venus that changed it completely. We don't know if we have remnants of ancient Venus. Could be these continent-like pieces, the Tessera, might not be. And so where Venus started, we talk about it starting as Earth, and has it always had this same sort of tectonic style? We don't know. Venus is very cagey about sharing its distant past, like that stranger in the bar who won't tell you where they're from. So we have a lot to learn about Venus.
All right, next question sort of follows on to that. Volcanism. Volcanoes also transfer heat from a planet's interior to its surface. Is Venus currently volcanically active? Does Venus display particular styles of volcanism, like we saw for the plate tectonics? And has its volcanic styles changed over time? And of course, where's the data to support the story? And volcanologist is the first speaker.
So A lot of the data that we use to try to understand the volcanic story on Venus is this Magellan radar data that was collected in the early 90s. So it gives us a radar image. It kind of looks like a black and white photo, but it's not. It's radar. So it's showing us things like roughness and smoothness. And what that shows us is that a lot of the volcanoes on Venus are very similar to volcanoes on Earth, particularly those volcanoes that ignore plate tectonics like Hawaii, that generate low slopes, lots of long runny lava flows. That's a pretty common volcanic style on Venus. And importantly, all of those lower smooth areas on Venus, the plains, those are all lava flows. And there are channels on Venus that are longer than Earth's Nile River, the longest river on Earth. Venus has longer channels. Venus is bone dry. Those are not water channels. Those are lava channels. Wow. We still don't know how that happens. I have lots of ideas. I'm happy to talk to you all about them later. But it's a mystery. And so Venus has a range of volcanic styles. What it seems to be lacking is the big explosive volcanoes like Pinatubo or Mount St. Helens, or the one that has so many syllables that erupted in Tonga. Those big explosions, they require water. And we've talked about other rocks that require water. And we don't see lots of evidence for that kind of volcanic activity on Venus. But it could be that it's pretty hard to see that kind of stuff with radar. So maybe once we get pictures, maybe we'll have a better view. And is Venus volcanically active today? You bet your biscuits it is. I'm out of time.
But not out of energy.
All right, and Dr. Filiberto.
Cool. So I agree with Tracy, especially that Venus is volcanically active today. Yes, no, I'm betting your biscuits. So one of the things that's weird about Venus volcanoes is just how big they are. On Earth, we have plate tectonics, which actually helps destroy volcanoes. In Vicky's image that she showed, there was the Hawaiian hotspot and there was a track of volcanoes, and actually it then curves and then gets subducted. So we don't even have the full track. On Venus, since we don't have plate tectonics, the mantle plume has stayed in one spot, pumping out magma after lava flow. And so the volcanoes, think about adding all of the Hawaiian volcanoes up into one, make an even bigger volcano. And so we've got giant versions of Hawaii all over the surface of Venus. We also have really weird things like pancake volcanoes and spiders, arachnids. Thank you. Arachnids. They look like spiders. They look like pancakes.
Very creative.
We have similar things on the Earth, but they're not that common on the Earth. And we see a lot of pancake domes. We see a lot of arachnids. We see other weird lava, long lava flows that just keep going, whereas on Earth, they stop. So it's pretty cool. What we see on Venus looks like the Earth, just larger.
You can just see the news report. NASA scientist says spiders on Venus.
Spider volcanoes, not spiders.
That's a big spider. Okay, so pretty clearly there's too much jocularity here. Venus is a fun planet. Who knew that not knowing could be so much fun, right? Okay, so a question, and this is going to be for Dr. Witten and Dr. Weller. Venus has a unique and globally widespread surface marked by distinctive deep-tailed topography, and it's called Tessera terrain. It apparently formed early in Venus's recorded history. How did Tessera form? And what might Tessera tell us about planetary processes that are unique to Venus, like the Tessera?
Okay, my babesies. I like the Tessera. They are very strange materials. As someone, one of the atmospheric scientists at the conference mentioned, they are wrinkled crust, basically. So high standing areas that are heavily deformed. They have very interesting textures. Initially, they were called parquet terrain because they look like parquet floors, for those of you familiar with the parquet floors. Anyway, like most responses I think I've given, we don't really know how they form, but there are two major hypotheses. So I'll at least cover one and let you cover the other one. So one of the ideas is that material from the mantle, the interior of Venus, is welling upwards to the surface, and it actually interacts with the brittle part of the upper portion of the planet. And so it kind of bulges it up and allows for some volcanic activity to occur, and it builds up these materials as they're erupting onto the surface. And then at some point that stops and it all kind of collapses, and you have this really wrinkly terrain, because you can imagine stretching and then removing the thing that's stretching the crust, and then it gets all crumbled up. So that's one idea. What's interesting about Tessera is we don't know what they're made out of. So geologically, in my mind, you have basalt, if you think about like Hawaii, and you have granite like your countertops. And those are kind of two end members. And we think that Tessera could be any of that. So it would be really important, the Veritas mission, Da Vinci, and Envision, all these missions that have been selected by NASA and ESA will look at what these materials are, because we don't really know the answer, and help us narrow down on, for instance, how can you make that much granite based on this idea of this upwelling material? Because based on processes that we know on Earth, it's very hard to do that. So I'll cut myself off.
Right. So the Tessera, they're weird.
Oh, weird.
They're really weird.
But cool.
They are really cool.
Mm.
Or hot. They're hot. So we don't know what they are. We don't know quite how they formed. They seem to be highly, highly deformed. And because they are highly deformed, and they also tend to be kind of below everything else. So all the newer stuff is piled up beside it and on top of it. That's why we think they're older. Well, the problem with the Tessera is they're defined by the fact they're deformed. And we're effectively saying, oh, this entire class of features are really pushed together, crunched up things. And because of that, we might have a lot of different materials, a lot of different behaviors, a lot of different formation mechanisms for them. Not all Tessera may be the same, or they could be. We don't actually know. So one of the interesting things as mentioned is that actually implies a lot of water. And if they formed 200 million years ago, had water at the surface then, which means we had two planets in the solar system, Earth and Venus, that had oceans. The problem is if they are granite, they're probably going to not be stable and melt pretty readily at the Venusian surface and near surface conditions. So we don't know how we can keep them if they are. But they also might be basalt, and some people actually suggest that they could be weathered. Remnants of kind of layered weathering, so almost like a sedimentary rock type situation, like water. So long and short is we don't know what they are. We don't know how they formed. We don't know what their material is, and we're trying to find out. And it will tell us a lot about Venus if we can do that.
Thanks very much. Okay, now we have a couple questions about upcoming missions. And the questions would ask are, what is the one priority observation or anticipated lesson you have for the recently selected missions, especially those of you that are on the missions? And what is the most important to you to answer, your most tantalizing question? And then the second half of that, going beyond the missions that are on the books, what would you like to see in your wildest dreams for Venus? And Justin Filiberto, Dr. Filiberto is our first contestant.
So I'm going to talk about Da Vinci since I'm a co on the mission. The thing I'm most excited about, even though I have talked about the rock record and the geology, is actually measuring the chemistry of the atmosphere, is getting high precision and high accurate measurement of the cloud deck, of coming through the cloud deck, seeing what's below the cloud deck, and specifically looking for elements that are out of equilibrium. So when we give you sort of a textbook of what the atmosphere is, that's the average equilibrium chemistry. What I want to know is what's out of equilibrium, because that tells us about where are the volcanoes. That tells us about what other things are perturbing the atmosphere that are changing things. And so I want to look at that out of equilibrium chemistry as we come through, and where is it within the sort of profile as we're coming down. So that's the thing I'm most excited for. And now I'm going to flip back to my geologist hat. Looking forward, the thing that is not on the table with any of the missions that are going in the next decade is what is the actual chemistry of a lava on the surface? We have data. So Vicky showed the picture of Veneer 13, which is actually my favorite picture and my favorite rock because it's weird. It's different than all the others, but it has really large error bars because it was taken 40 years ago. So I want to go to a volcano, measure one of those nice long lava flows because they're flat and we can land on them, and get a high precision, high accurate measurement of what is the lava, what is the rocks made of on the surface of Venus, because we don't know.
You done? Okay, Dr. Greg, what would you most like to see?
Talk longer.
Don't worry, if you talk short, there's more time for the audience.
Okay. So what do I most want to see? Oh, okay. So I got very excited about Justin's answer because as a volcanologist, of course, I want to know what the composition of the Venusian plains are and the lavas. The plains make up most of the planet and we need to know what those are. But if I had to choose, if there was only one place on the surface, I would go to one of these tessera. I want to know what the tessera are. Even as a volcanologist, I want to know what these are because knowing what these really deformed, possibly ancient, maybe not, terrains are would tell us so much about that ancient history of Venus or not, which would also be really cool. Yeah, I think tessera the composition of the tessera would be my first choice. And then the lava plains, absolutely my second choice. And then in my fantasy world, moving forward, we would have, I mean, what is Venus, right? But everyone's fantasy world. I would have a global network of instruments to detect quakes, Venus quakes. Oh, thank you. You can give me that $20 when we're out. Because what Mars has shown us with the InSight mission is that even just having one instrument that can read the interior pulse of a planet gives you incredible information about the interior heartbeat of that planet that you can't get any other way. And if we had 20 or 10 of these all over Venus, which is volcanically active, and I am still betting my biscuits, we would get a series of quakes, maybe every day, that would give us essentially a CAT scan of the interior Venus. And that would be thrilling beyond my wildest dreams because I'm that kind of a person.
Dr. Weller.
Proper alphabet.
Well, I'm in a quandary because I'm excited by both of your answers. So.
But
if there
what's
was-
your answer?
Holding my feet to the fire. All right. So if there's one thing that we have to know about Venus, and we only had one thing, it's what Justin said. It's the atmospheric chemistry. It's the disequilibrium. It's how active it is, what's going into the atmosphere, what is the atmosphere made of, all the way down. Have that column. We have a sample from a Russian mission where we have an atmospheric column. It dropped down, it went to the surface and crashed, but it got data. It's missing data, but it got data. We have some missing records. we need that, and that is happening with Da Vinci, because we need to know, is the atmosphere changing? If it is changing, how much is it changing? Is it out of equilibrium? If it's out of equilibrium, it is a highly dynamic planet, especially with an atmosphere that is that thick. And as I said earlier, the atmosphere is the time integration of the entire planet. So if you want the most bang for your buck, it's got to be the atmosphere. And I say this as an internal mantle person. But now, having said that, we also need to, and I'm going to cheat and choose multiple things. We need the Tessera because we need to know what they are, but we need more than one. We can't do one. It would be like dropping on the Himalayas and saying, haha, this is all of Earth. It's snow, clearly. We have to be careful with that. These small sample sizes, we need to see what the Tessera are, and we need to see it in more than one place. And we're going to get wonderful data from Da Vinci for this. And now I'm going to make Tracy happy. We need the basaltic plains. And we need that because it's 80% of the planet. 80% of the planet is covered with basically Hawaii-like volcanism. It's coating the entire planet. And that tells us some truly remarkable fundamental things about the interior. We can figure out how hot the interior was when it melted. That tells us when Venus lost heat and how tell what the planet is made up from, how much heat is left over from accretion, how many radiogenic particles are left in the planet. All of these things we don't have any good constraints on. So we need the entirety of the surface is really what I'm saying here. And we need a campaign to sample all of Venus. Field trip to Venus. Sample return to Venus. Yes, that is what we need. And but you know, I think we're building a facility here to curate sample returns nearby, in fact. But yeah, we don't need a decade of Venus. We need a century of Venus to understand it. So the pie in the sky is to have a robust scientific campaign to do for Venus what we're doing for Mars right now. So much, we're starting to get so much more information from Mars because we have continuous missions, because it's kind of easy to do. And we have stuff sitting on shelves and we put them together and send them off, and it's relatively inexpensive and we get a lot of bang for our buck. And if we start developing this for Venus, which we're starting to, probably do the same.
All righty, my turn, huh? Okay, I will just pick D, all of the above. No, but I do have my own preferences, I promise. So if I have to be really realistic about things and think about these upcoming missions, something that I'm really excited about because I study Tessera is the Veritas mission and also the Envision mission. They have an instrument that's called VEM. And it is going to look at the surface and do these global maps of rock type. And for me, understanding composition or mineralogically, I guess, the difference, or lithologically, the difference between Tessera is really fascinating. You look at these parquet terrains and they don't all have the same parquet pattern. They have lots of different patterns. They have lots of different brightnesses. And it would be weird if they were made out of the same stuff, frankly. But we don't actually know, and we don't know which ones are different from one another. So I think these upcoming missions, you know, Veritas, Envision in particular with this VEM instrument, will be able to answer that question. But then that's just going to open our Pandora's box for us, because we're going to have a million more questions about it. So my pie in the sky, what I want to see happen is I want to see some landers on the surface. Yeah, I want to see a lot of them. And I want to see them measuring the planes and the Tessera, like I already said. But I want to see them be long-lived. You know, there is technology that's being developed, really cool stuff like diamond discs to help transfer power across these electronic systems. You know, really, really awesome things that are on the horizon, and we will see them here, not in this decade, but in the decades to come. And so that's something I'm very much looking forward to, is understanding the surface chemistry, because that tells you so much about the interchange between the surface and the atmosphere.
Thank you very much. I just want to point out that we have images, Magellan images that you can have out in the lobby. And one of them is of this Tessera stuff. So you can just, no matter where you are, I can see that this is a mess, whether you're close or far away. This is a mess, but this is the kind of terrain that they're talking about.
Looks like modern art.
Jackson Pollock.
Yeah, yes.
Okay, so. Yeah, anyway, but those are available as soon as we're done with the question and answer here. And so please go out and find some good ones. And now we have question and answer from the audience and online also. And who is going to be waving the microphones around? Is that you, Andy? Okay.
If you're on the other side of the room, I'll probably throw it. So just be prepared.
We have a question up here, I believe.
This is the first time I have so much fun listening to scientists discussing their work. I mean, this is amazing. Now, I understand that Venus mass is 83% that of Earth, give or take. And Sister Earth is jealous. She wonders. Now, Sister Earth knows that the rotation of her sister is much slower and the wrong way. And what gives? Okay, it cannot possibly be exercise. It's got to be diet in the last 3.5 billion years.
I know. So why Venus rotates backwards? I'm gonna steal an answer from something everyone else has said. We don't know. We have a lot of models. They all answer some things, not everything. We really don't know why Venus goes backwards. Oh, why is Venus slightly smaller? Every planet is slightly different size. They create different materials. So this is something Matt talked about with maybe the Earth created more water. Mars is a lot smaller. Jupiter and Saturn are a lot bigger. Every planet has slightly different building blocks. And so that can explain why they're similar, but not quite the exact same.
I can toss in a little bit about the rotation. All the planets, almost all of them rotate in the same direction, sort of the same way as the sun does. There are a couple that are different, that are tipped over. Those are all blamed on impacts, asteroids of some size, hitting them, tipping them over. That's probably the best idea that's out there for Venus, that somehow there was an impact on it that despun it, somehow took away all of its spin. Why that happened is very, completely unknown. It's really peculiar. It spins very slowly. It's not like the moon that always faces the Earth. It does spin compared to the sun. And as Justin said, it spins backwards, which is really weird. So it's a wonderful question, and maybe we'll figure it out someday.
She's an independent woman.
Yeah. It's got her own spin on things.
Okay, I have a question. Why is granite related to water? You said they get this together, yeah.
Sure. So on the Earth, when you melt the interior, if you melt it without a lot of water around, you make basalt, which is what we see at Hawaii, we see at Iceland, we make lots of lava flows. The more water you start adding to things, like when we're in a subduction zone, what comes out of Mount St. Helens is not necessarily basaltic, it's called an andesite. And so as you add more water to the interior, as you start remelting the crust and subducting things, the silica content goes up. And so correlation with how much water is around in the water cycle with the silica content that are made in a magma.
And granites have more silica.
Sorry, I missed that jump. Apologies, yes.
We can translate.
Granites,
once in a while.
apologies.
Yeah. And there's a really famous paper in the geological literature titled "No Water, No Granite, No Oceans, No Continents." Doesn't need a conclusion. Okay, yeah. Yeah.
So I have a couple questions. First, do the surface conditions, 900 degrees and the pressures, do those sort of have affinities for compounds that are not, in terms of the chemical compositions of compounds different because of the temperature and pressures? And then the follow on is Venus losing a lot more atmosphere because of the high temperatures and pressures. Earth.
All right, so yes, the surface of Venus, on Earth, we call it metamorphism, where one rock is changing into another. And the surface conditions of Venus are, for Earth, metamorphic conditions. So the rocks, the lava rocks should be coming out in contact with this hot, high pressure, caustic atmosphere and changing nearly immediately. And so the rocks that we're talking about, and if you looked at the Veneer 13 picture, everything sort of had this, well, the atmosphere is yellowish, but if you looked at the rocks, they sort of have a reddish tint to them. And that's the rock, those lavas changing in equilibrium with the atmosphere. So that's the rocks. Yeah, so that's the rocks. But the rocks are, because they're also changing the atmosphere. There's exchange between the two. And so the flip of that is Venus losing its atmosphere? Correct? Was that the second half of your question? Yeah. So that was the second part. Oh, so sorry, I misunderstood that. So what are the compounds in the atmosphere itself? We have similar gases that come out of volcanoes. So sulfuric acid, hydrochloric acid, sulfates. Yep, those are happily floating around. It's a very caustic, very acidic atmosphere that wants to eat our rocks and eat our landers, which is why the I'll answer the first half of that, and Matt, I'm going to give you the second half of where did the water floating off part. So yes, the compounds in the atmosphere are, well, question, and what one of the things Da Vinci is going to answer is, are they in equilibrium or are they out of equilibrium? If they're in equilibrium, it tells us this nice big atmosphere is in. And so the compounds that we would expect are there. If they're out of equilibrium, which is what we're going to look for, then it tells us something is perturbing them. Lots of things can perturb chemistry, volcanic activity, on Earth biology, lightning, meteorite impacts. There was a nice cartoon that she showed of everything going on the Earth, of things going up and down. That all perturbs our atmosphere. And so that's one of the things we're going to look for. Now, the water loss, I'm going to hand over to Matt.
So yes, the water loss. So one of the arguments for what happens with water is you have photodissociation. You have UV coming in, it comes in, it just pretty much takes a baseball bat to your water molecule and knocks the hydrogen clean off. And eventually what's left, the OH that's floating around, what's left of the water molecule will go someplace. Necessarily. There are arguments that it kind of goes into weathering of the surface, or there could be other chemical reactions. In the hydrogen, which is lighter, the argument is that it floats upwards and then it's easier to strip off. So Venus being closer to the sun, you have strong solar wind and you have a lot of interaction. So there's a lot of loss of material that way. And it used to be thought, and it's actually argued right now that because the Earth has a magnetic field, it shields us. We keep water because of it. There's challenges to that line of thinking recent decade or so. And in fact, observations of Earth and Venus show very similar loss rates. in the atmosphere. So it's an open question then if you can actually lose that much hydrogen to space, which is kind of the prevailing wisdom for where the water goes. Then it's if the water is not being lost to space, where is it? Or was it even there? And these are trying to answer with these missions and hopefully a century of new missions.
I got a question online asking, are there any plans to build a spectral library for Venus and create a comparison to spectral signatures from Earth?
Yes, there is a plan. It is actively ongoing. There is a fabulous lab in Germany run by Jorn Helbert, and he is working with several scientists here in the US. Darby Dyer is one of them, and they have been collecting rocks from everybody who will give them rocks, and they are measuring them in their lab at the temperatures relevant to the surface of Venus, because the spectra or the response of these rocks to at different wavelengths is different at high versus low temperatures. So it's very important. We can't use the spectral library as the information that we have for the moon or Mars, because those rocks are at different temperatures, and the signatures that they give off are different. So yes, there is active work going on to build the spectral library.
I guess this is kind of back on this process of, well, you have the, I guess, the disappearance of water, if it existed. And then there was also the question about the magnetic field, whether it exists or not. And assuming that there wasn't a magnetic field, it would be possible if the worked as a deflector, that it might take the deuterium as well. It seems like a lot of the heavier isotopes might disappear as well. And then isotopes, it would be a measure of how fast this atmosphere is disappearing. Why doesn't it have a magnetosphere? Oh, I know the answer. Never mind. No,
That's not true. That's not true.
So that's a wonderful question, actually. One of the issues is we don't fully understand why the Earth has a magnetic field. Ganymede has a magnetic field, the Earth does, and the giant satellites do as well. Generally speaking, hot metal moving really fast will generate some form of magnetic field. But the Earth is kind of an open question for why we have as strong of a magnetic field as we do. And Venus doesn't seem to have currently. Whether or not that was true in the past is a very open question. Some of the ways you could prevent a magnetic field from generating is if you have a heavy atmosphere, well, if you have a heavy hit, yeah, if you disturb the system with a large impact, you could stir it and it could. Another way you can do it, though, is if ultimately a lot of the magnetic field is thermally generated. So heat coming out of the core causes
In fact, there was a talk exactly about this at the science conference. Was it yesterday? I think it was either yesterday or this morning. And the question is, there might well have been an early magnetic field, and one of the suggestions was to send magnetometers there to look for it. The fact is that there's none detectable now from orbit, but we can't really get all that close to this planet. The really thick atmosphere. There's a very strong interaction with the magnetic field of the sun. I don't think anyone here is competent to talk about that.
But to have a magnetic field, you need turbulent flow within the core. And so we need an inner and outer core. We don't know if we have an inner core on Venus. And then, as you alluded to, sir, the rotation is really important. And so it could be that we have a proper enough inner and outer core to allow for turbulent flow, but because Venus is rotating so slowly that there's not enough disturbance, and that if it's essentially laminar flow, we're not going to have that magnetic field. And right now, we can kind of say, we know the basics that we need for magnetic field, and Venus presumably doesn't have those, but why not? But rotation could indeed be a reason. Yeah, and that's because on that graphic, we know that the Earth has an inner core and an outer core, and the inner core is solid and the outer core is liquid. And in that liquid outer core is where we have turbulent flow, and that's where the magnetic field is generated. On Venus, we know we have a core, but we don't know if we have an inner core and an outer core, or if we have an inner core, how big those are. So we do have a core, but we don't know if we have the two parts to the core. That's the core of the question.
And to figure this out, we need the seismographs that Jenny was talking about.
Who's been very patient.
Hi, Megan Russell, Planetary Science Institute, Colorado. Let's suspend reality for a second and pretend that. Yeah, let's pretend that I have $1 million in prize money for someone to show me indisputable evidence that Venus is volcanically active today. But we can't get in, you can go and get data, but you have to sort of hedge your bets based on the data that we already have. So where would you go? Where would you look and what evidence would you show me?
$1 million?
Not enough, not enough.
Even close.
That's over and above the mission money.
That's just a
Not
bonus for answering
even
the question.
close.
That's not to pay for the mission. That's for your retirement fund, Tracy.
Yeah, there we go. So we're just gonna set aside the dollar amount because, but I'll answer the where would you go question. And there have been a couple of places on Venus that have already hinted to us that they have erupted in the last couple of decades. And one of them is called Iden Mons, and the other one is oh shoot, is it Matt Mons? It's actually Maat Mons. There's there's an apostrophe in there. That's yep, Maat Mons. And they from orbiters that were not designed specifically to look at the surface of Venus, but still were able to manage to do so at peer through the clouds at a very specific wavelength. Essentially, these two volcanoes glowed, and they showed us that they were warm. And remember, the surface of Venus is already hotter than the hottest setting on your oven. And so if there's a volcano that is hotter than that, that's a good signature that it's been active. So I think those are the best choices. And some of the work that Justin has done, looking at how fast olivine crystals weather. Setting you up.
Thank you. So, lava rocks on the surface of Venus should alter very quickly. And from orbit, they should look like an altered rock and not a fresh lava. And at Iden Mons, which is the volcano we have the most data for, we see these lava flows that have a very, very fresh signature, as fresh as some of the freshest lavas on Earth. But the lava rocks should alter really quickly. And so that says that they're really young. Part of the debate is how young is young? Are they days, weeks, months, years, decades, tens of thousands of years? We don't know, but that's still volcanically active, whether they're tens of thousands of years old or they came out yesterday. So I'm going to repeat, my favorite volcano is Iden Mons because I've worked on it for the last 5 years a lot. And we have a huge amount of data. So repeat measurements over Iden Mons and getting down to these lava flows would be amazing, but it's cost probably a few orders of magnitude more than $1 million to do that.
I'm just going to add to that a little bit and kind of pick a bigger area. So there's a region of Venus that's kind of triangular. It's called the BAT region, which is just fun. It's Beta Atlas Themis. It's an acronym because it's NASA, right? There's always an acronym. There have been, in addition to the volcanoes that Tracy and Justin mentioned, there have been some indications above regions within the BAT area of changes in atmospheric composition. temporary changes. And so that is a suggestion that there might have been a volcanic eruption of some kind in that area. The Beta Atlas-Themis region is large, but it is also an area that has the highest concentration of volcanic landforms on the surface. So that's a really good area to go. And for example, with Veritas, you could do repeat imagery. The really exciting thing about these missions is we have the Magellan data from the 90s. And if we think it's active today, which I think I can safely say everybody up here agrees that Venus is volcanically active, and we're taking images again, 30, 40 years later, the surface will have changed. And so we might be able to see changes in the shapes of landforms or the brightness of the landforms. And so in addition to looking at compositional changes, so another signature that Veritas is going to look for with them, the them instrument is for signatures of water on the surface or near surface. And so that's just another piece of data that you could use to indicate that there might be active volcanism on the surface today.
And I want to clarify a little bit, as a terrestrial volcanologist, because I'm on Earth, which is a planet, we define a volcano as active on Earth if it has erupted sometime within the past 10,000 years. So to a terrestrial volcanologist, active does not mean it's going to kill you today. It means that it erupted sometime since the last ice age. Whether that's appropriate for other planets, we are not sure yet, but I just want to be clear, when we say active on Earth 10,000 years, I am absolutely certain that by that metric, Venus has been popping its top for a long time.
Oh, okay. You said Venus doesn't have plate tectonics, or at least not as we know it. Why? Or am I asking, why do we have plate tectonics? Why
Okay,
are
so
they
you have to
different?
leave the hardest question for last. So we don't know.
I came out here on a cold night and I'm hearing
I
that.
know, I'm like the broken record. So, thanks for that. So we don't know why we have plate tectonics. We don't know how plate tectonics initiates. There are some ideas for how plate tectonics might initiate. An exciting thing that I didn't actually mention when we were asked about tectonic regimes is recently in the literature, it has come out that people believe that there is subduction occurring on Venus, but it is not subduction like we see on Earth. So there are these totally awesome, totally weird and unique landforms to Venus called corona. Yeah. Not the beer. Yeah. And there are these circular landforms that tend to have some sort of topography associated with them. But there have been physical models. So people have like tanks in their laboratories where they've used some sort of silica fluid to model Venus. There have been models, numerical models to suggest that you can have hot material upwelling towards the surface, erupting onto the surface, and then the surrounding crustal materials will slowly get bent down into Venus and then kind of subduct or fall into the mantle. So there is like a flavor of Earth plate tectonics going on there with subduction, but it is much more localized than what we see on Earth. And yeah, sure.
Well, I think we have to be really careful. There is not as I said, that I'm going to disagree.
Sure.
Because these guys are too agreeable. But plate tectonics has a real definition. Subduction has a real definition. We take the lithosphere. That lithosphere is recycled from the surface down into the mantle. And we can actually see it go all the way to the core mantle boundary in places. That's what subduction is. We can't say, oh, something took a little dip and call it subduction and say it's not like Earth subduction. Then we could just call giraffes, dogs, but they're different from one another. And so we have to
A
be
little extreme.
really careful. And subduction has a definition on Earth, and plate tectonics is truly a global concept that involves the entire lithosphere and recycles things from the mantle. And so I want to be really careful. We all love plate tectonics, and it's amazing in what it does for our planet, for our resources, but you can't go halfway with plate tectonics. Then it's not plate tectonics anymore. And subduction, we can come up with another word, but we can't say we have subduction, but not like subduction on Earth, because then we don't know what we're talking about.
Or we can call it subsumption if we want to talk about Europa. I'll employ that word. But so we don't know. So there are some ideas that if you have your lithosphere, the brittle part of a planetary exterior that is cold things are heavier than hot things. And so they might be a little bit more brittle as well. And so you could have them breaking and potentially sinking in some particular kind of stress regime. And you might be able to, once you've started to have something go into the mantle and it continues, it can sort of pull the stuff on the surface down with it, and you can kind of begin a cycle. So that's like one idea, but we really don't know. I don't know if anybody else wants to. Matt, go ahead, or Tracy.
We're going to make it really quick, Matt, really quick.
Really quick. Okay. So actually, it's a really great question that you asked, because we don't know what early plate tectonics on the Earth even looked like. We don't know if it could have looked like Venus. Venus could be a proto-state for the Earth. As Vicky was saying, plate tectonics is very organized and defined, but it doesn't pop out of nowhere. It has to develop somehow. And we don't know what that evolution looks like because we're kind of missing large chunks of that on the Earth. But one thing that's really interesting is there's been a body of research that I've been involved with over the last decade that has shown that increasing surface temperature, so a runaway greenhouse effect, actually can stop plate tectonics from operating. So if you crank up your surface temperatures, you actually stop the planet from behaving in a manner like the Earth. And that means that the climate actually can control what happens in the solid Earth and also the expression at the surface, and fundamentally change how the planet operates. And maybe we're seeing that on Venus, maybe we're not, but that's something that we're actively pursuing, trying to understand.
No, Tracy, I'm going to let you talk for 45 seconds. Yes.
Earth is the only planet in the solar system that has plate tectonics, water that can exist in all three phases, and life. And there is a body of work out there that suggests that those are all related, that subduction is enhanced with the presence of water and sediment that was generated by living organisms that then died. So Earth is really special, and looking at Venus helps us remember that.
I will just reiterate what Tracy says. Water is the key. That there's a lot of new models that show water is needed. It lubricates the interior. It helps with subduction. It helps with de-gassing of magma, the explosive volcanism, life. So water is unique on the surface of our planet.
All right, so now you guys are experiencing what it's like during the day. We don't like to shut up and we don't want to leave. And you don't have to, actually. So actually what I just want to do is transition us from being in here to going out to the reception. Before we do that, I just want to thank our panelists and our moderators. It's been a fantastic night. Also, if you've been involved in any Venus mission, Da Vinci, Veritas, Venus Express, Akatsuki, or Bepi Colombo, can you stand up, please? Or Pioneer Venus, or Magellan. Do we have any veterans? No, okay, I think they're still back home. Now, Moscow's not home, but for 4 years, I went there every 3 months, so it has a close place in my heart. So anyways, we're gonna go out to the reception. Those people that just stood up, you can bombard them with questions along with the rest of the panelists in a less formal way. But Thank you for coming and have a great night. Also, feel free to take pictures out with any of the banners of the missions.
Good success.
And your intro was so good.
Wow, what a good thing that you put together. Yes.
That's why I'm in it. You know, it's certainly not for the money. Yeah, that's one of those $64,000 questions. Well, that was damn fun.
That was, good job, Alan.
Yeah, that worked really well, didn't it?
I think it did.
Yeah, lots of good questions. I think the only thing we could have done better was with that picture, when they're talking about volcanoes in Tessera. It would have been really cool if we had been able to shine something up on the screen. But that's,
That's for next time, right?
yeah, that's a lot more like, oh, yeah, slide six.
Well,
It could have been.
well, if we had the questions ahead of time, so we could have.
Yeah, that we could have. It just didn't.
Yeah, I didn't, and another thing too is that projector screen on, if you're as tall as me or taller, it blinds you.
Yeah.
So
Okay,
that's,
not
there's
gonna
that
work.
too.
Yeah. What we need is a projector that used to be in back of the wall there, so it could be projected.
Or what we need are just big screen TVs on
Yeah,
both sides,
that
right?
would be-
That's
yeah,
all, that's what we need.
that would.
That's what we need.
Congratulations. Depends who's at all.